Okay, so before we get to proving that Q is listable, let's go through a few definitions. So a set A is called countable. A set A is called countable or listable, and we want to probably use the word listable. They mean the same thing. Listable makes more sense to me, so I'm going to start using this word. So a set A is called listable when there exists a bijective function from A to N, or N to A, because I should do N to A. If there's a bijection from A to N, then there's a bijection from N to A, but we're going to do it from just N to A. And the best way we're going to say, so we could have, what's a good example? We could start with A being the natural numbers themselves. And of course, the natural numbers are listable because I could sit here and I could define this function. So 1 goes to 1, 2 goes to 2, and then so forth. And I could go on forever and ever. And this indeed will be a bijective function from N to N. You could also put the evens in bijection with the natural numbers. So if you have 1, 2, 3, 4, 5, here's the natural numbers. This is over here, 6, 7 going down. And then you have the even natural numbers. So 2, 4, 6, 8, 10, 12, 14, 16, so forth and so forth. You can put them in a bijection like this. And you should see that this function is indeed injective and surjective. Every single number will get hit, and every single number will get hit exactly once. Or every number will get hit at least once, and every number will get hit at most once, right? That's the idea behind injective and surjective, right? Injective means that every number is hit at most once. Every number in the codomain, every number in here is hit at most once is injective, and then every number is hit at least once is surjective. And when it's both, every number is hit exactly once. Now, okay, we want to talk about just the set of positive rationals. So this is positive rationals. So the set of positive rationals are all the numbers that can be written as the division of two natural numbers. And this set here gives a good definition of what the positive rationals are. Some examples of just a positive rational would be, right, like you got 1 over 2 because 1 is a natural number and 2 is a natural number. You got 3/4 because 3 is a natural number and 4 is a natural number. So then 3/4 is a rational number, a positive rational. You could have, I don't know, whatever, 101 over 103, another rational number. So here, these are all the rationals. This set right here. And those are a few examples. Now, let's go and let's prove that the positive rationals are indeed in bijection with the natural numbers. Therefore, they are listable. So here, what I've done is, in this grid, we should see or convince ourselves that every single positive rational will be listed here. But the thing is, we do want to be a little careful. And what we want to do is we want to just be careful in how we define this bijection. So 1, I'm going to send to 1 over 1, this value right here. So this is 1. Okay, then I'm going to take 2, and I'm going to send it right here to 2, which is fine. 2 over 1. Then I'm going to say 3 goes to this number over here. And each time I do this, I just want to check, right? This is 1/2. I just want to check, have I hit this number before? Is there any equivalent number in the list? No. But then I could go down, and then 4 is going to go to a third. But now, you see, this number I don't care for. Why don't I care for this number? Because I've already hit 1, so I just skip it. And I go to 3 over 1. And I'm going to say 5 goes to 3 over 1. instead of it going to 2 over 2 because I've already gone to 1, because I want it to hit every single unique rational once. So I just need to find the first, right? So I skipped over this here because this I've already hit. This is 1. This is 2 over 2. So I've hit that rational already. Then I'm going to go to 4 over 1 with 6. And I'm going to keep doing this. And then 3 over 2 I haven't gone to. And then 2 over 3 I haven't gone to. And then 1/4 I haven't gone to. 1/5 I haven't gone to. And I just want to do this until I illustrate that. You see, I'm going to have this 2/4, but I already hit 1/2. So I'm going to forget about this. And I'm just going to skip and go up. I'm going to skip this one. And what else am I skipping? I'm skipping this one. And I'm going all the way to 5 here. And that's the idea, right? This was a good example to illustrate. Then I'm going to go to 5 over 1. And you see, I could sit here and just cross out the rationals that I've already hit on this grid as it is that I go and define this bijection. But basically the point is that if I keep going in this snake-like manner, right? I keep going here, and then I ask myself, have I hit 5 over 2? No. So then I put 5 over 2 on the list, and then I keep going. 4 over 3, right? Eventually, right, I will list every single unique rational number. 3 over 4, I don't think I've hit. And then 15 and so forth. I'm going to go to 2 over 5. And then 16, I'm going to go to this number. I have to be careful. 16, this is 6. This is 1 over 6. So it's 1 over 6. I haven't gone there. But then when I go down, what am I going to get to? I'm going to get to 7, 1/7, which I haven't done either. But let's just illustrate how it is that when I go back up. So then I'm going to get over here, it's going to be 2/6, but that's 1/3. And I hit 1/3 here, so I'm going to skip over this one, right? And 18 is going to go to 3/5. And then 19, nope. And then 5/3 is 19, right? And what's key here is that you should see that eventually every single rational number will be listed here, and it will be listed exactly once. That's the key point here. And this is a way to define a bijection from N to Q. Given some Q, I'll be able to find it in this list eventually. And this is a bijection. And this defines a bijective function. Where f goes from n to the positive rationals. Now you might say, what about Q? This is an easy task, right? What would be the trick with Q? Well, I have this, right? So if I made another one, I could just say that these are the negatives, and then all the negative Q are hit. We want to include 0 too, so there's just a nice way to compensate for all of this. We could just send the evens, we could send this 2, 4. I could go 2, 4, 6, and send all the evens to these numbers, right? So 2, 4, 6, 8, 10, 12, and then so forth, and send all the evens to one, the odds to the other, but just shift over maybe for 0 for one of the lists. So just start this list at 0, 0, 2, right, 4, and then so forth. And then now you've hit all of Q. And all of Q is, instead of you taking possible numbers from the natural numbers, you take numbers from the integers. So A over B, where A and B are now not just natural, but they're in Z, and B is not equal to 0. Can't ever divide by 0. And then that's the positive and negative rationals and 0, because A could be 0. And that also is listable by the argument that I just made, that I could use this trick again with just the evens and start it with 0, so you have 0, and then or you could start, actually you could say 0 here, and then you could go, this will be 2, this will be the 0 number. You could just put a 0 here, move everything down in A, because the natural numbers don't include 0. But okay, it's okay. I mean, the list just starts 1, 2, 3, 4, 5, 6, and then you should also convince yourself that every single 0 and every single positive rational will be on this grid, and then you just make the same grid again and you say you map the odds to that grid, and then just call one grid the negative rationals, and then one grid the positive rationals, and now you have a bijective function from N to all of Q. But either way, it's clear to see that there's a bijective function to the positive rationals, this here. And this shows that Q is listable.